Hello and welcome. My name is Syed and I have created this course of statistical data analysis using R. You might wonder why we need data analysis. Well, we live in a data-rich world. Data is revolutionizing businesses in many ways. Companies are using data to understand their customers better. The insights gained from analyzing data is helping companies identify growth areas. Statistical learning refers to a set of tools for modeling and understanding data. Statistics is a study of how to collect, analyze, and draw conclusions from the data. Statistics involve identifying a problem, collecting relevant data, analyzing data, and form a conclusion. R is a popular programming language adopted for data science and statistics. The R programming language is used by professionals and data experts around the world for modeling financial data, mapping marketing trends, and other analysis. And the best thing is, R programming language is free. This course of statistical data analysis is the best way to start learning data analysis and getting handy with R programming features. In this course, we will learn about qualitative and quantitative data. Moving forward, you will acquire knowledge about mean, median, quartiles, variance, and standard deviation, and where these descriptive statistics concepts are applied. Eventually, we will look at bivariate and multivariate data, as well as we will learn about probability distribution and hypothesis testing, which are one of the most important topics in inferential statistics. Each of these sections include screencast of hands-on application and implementation. R is an open-source statistical programming language supported by a vibrant community. R is also called a language for statistical computing. R runs on almost any computing platform and operating system. R provides a rich collection of statistical techniques or functions and has sophisticated graphical and visualization capabilities for plots and graphs. This language also provides complex visualization of high-dimensional data. Another very important feature about R is that it is highly extensible. In this course, we will also cover the R's basics and programming fundamentals, as well as R data structures such as vectors, matrices, lists, and data frames. Finally, we will look at how to import data from various sources and how to handle large data sets. And on top of that, in this course, we will move deeper into the graphical capabilities of R and learn how to create visualization, which will help in analysis. In this video, we will look at different kinds of data and talk about the ways of obtaining that data. That is, we will speak about the population and samples. The very first aspect in statistics is obtaining the data. Let us say that if you are hungry, you have to find the food first. In the same way, if you want to analyze data, you need to first obtain the data. There are different ways of obtaining data, but the most important is the observation and experiment. Let us consider a simple example. Which kind of pizza is more popular? It would be easy to gather all the information if all the pizzas are sold at one place. However, this is not the situation, since there are many different eating places where you can find or buy pizzas. In this situation, the best choice is sampling. The question is it possible to estimate the small piece of sampled information, that is pizzas, to the whole big population of pizzas sold at different locations? Statistics could answer this question. Statistics is a form of mathematical analysis that uses quantified models, representations, and synopses for a given set of experimental data or real-life studies. A lot of data used by mathematicians, academicians, statisticians, researchers, marketers, and analysts, etc. are actually samples, not populations. A sample is actually a subset of a population. The objects from which we have measurements or observations form a sample. In contrast to this, a population is the set of all objects that had the same chance to become part of a sample. In principle, there are two different sampling strategies. Random sampling, which means that the individual objects for measurements are selected at random from the population. For example, climate data, stock prices, etc. And stratified sampling, which requires that the population is divided into subpopulations. These are separately sampled and the population characteristics are estimated by using mean values. Let us now talk about different kinds of data. Data can be classified into qualitative and quantitative. For qualitative data, we need to look at the question that is it possible to represent data in zeros and ones? If it can be represented in zeros and ones, then we can call it as a binary data, or else we can call it as nominal data. Example of a nominal data can be gender, which can be represented as male and female. Or we can also have shoe sizes, which is a labeled data. The second classification of data is the data result of a measurement. Here the data can be of two types, continuous data or discrete data. This type of data is known as quantitative data. In this video, we will talk about statistics, more specifically about the type of statistical methods, different statistical measures, and categorization of descriptive statistics. Statistics is a form of mathematical analysis that uses quantified models, representations, and synopsis for a given set of experimental or real-life data. Statistics studies methodologies to gather, review, analyze, and draw conclusions from data. There are many different types of statistics pertaining to which situation you need to analyze. Statistics are used to make better business decisions. Some statistical measures include the following. Mean is a mathematical average of a group of two or more numerals. Mean for the specified set of numbers can be computed in multiple ways, including arithmetic mean, which shows how well a specific commodity performs over time, and a geometric mean, which shows how the performance results of an investor's portfolio invested in that same commodity over the same period. Regression analysis determines the extent to which specific factors such as interest rates and the price of the product influence the price fluctuation of an asset. This is depicted in the form of a straight line called linear regression. Skewness describes the degree a set of data varies from the standard distribution in a set of statistical data. Most data sets, including commodity returns and stock prices, have either positive skew or negative skew. Variance is a measurement of the span of numbers in a data set. The variance measures the distance each number in the set is from the mean. Variance can help determine the risk an investor might accept when buying an investment. Statistics is a term used to summarize a process that an analyst uses to characterize a data set. Statistical analysis involves the process of gathering and evaluating data and then summarizing the data into mathematical form. Statistics is used in various disciplines such as business, social science, etc. Two types of statistical methods are used in analyzing data: descriptive statistics and inferential statistics. Descriptive statistics is used to summarize data from a sample exercising the mean or standard deviation. Inferential statistics is used when data is viewed as a subclass of a specific population. Let us now discuss descriptive statistics. Descriptive statistics is brief descriptive coefficients that summarize a given data set, which can be either a representation of entire or a sample of a population. Descriptive statistics are broken down into measures of central tendency and measure of variability or spread. The measure of central tendency focuses on the average or middle values of data set. whereas measures of variability focus on the dispersion of data. These two measures uses graphs, tables, and general discussion to help people understand the meaning of the analyzed data. Measure of central tendency include mean, median, and mode, and describes the center position of a distribution for a data set. Measure of variability includes the standard deviation, variance, and the minimum and maximum value as well as skewness. Measures of variability or measures of spread aids in analyzing how spread out the distribution is for a set of data. While the measure of central tendency may give a person the average of a data set, it does not describe how the data is distributed within the data set. In this video, we will talk about qualitative data. In R programming language, data is generally stored as vectors or data frames. Of course, there are several types of data that we might need. The qualitative data, which is also considered as categorical data, can be stored in R programming language using factors. And the quantitative data or continuous or numerical data can be stored in R programming language using numerics. In this video, we will consider the qualitative data and learn how to work with them in R. Qualitative data is non-statistical and is typically unstructured or semi-structured in nature. This data isn't necessarily measured. Instead, it is categorized based on properties, attributes, labels, and other identifiers. Generating this data from qualitative research is used for interpretations, developing hypotheses, and understanding. Qualitative data will almost always be considered unstructured data. The qualitative data cannot be collected and analyzed using conventional methods. Some of the real-time examples of qualitative data are categorizing gender based on properties, that is male and female, categorizing shoe sizes based on labels, and ratings for a product based on some attributes. In this video, we will practically look at how to handle qualitative data. Let us take an example of sizes of shirts. So we will create shirts as an object, and using the assignment operator and C function, we will assign different sizes as the elements of the vector shirts. Let us consider we have S for small size, M for medium size, L for large, XL for extra large, XXL for extra large, and so on, so forth. Since the labels S, M, L, XL, XXL are all characters, so therefore every element of this vector will be in single quotes, and the vector shirts is considered as a character vector. In the next statement, we will display the elements of the shirts vector. Let us execute these statements. You can find that we have the output which displays the elements of the shirts vector. Let us create another object that is shirts underscore sizes, and with the assignment operator we will also use factors function, passing shirts as the argument. This statement will create shirt underscore sizes as a factor. In the next statement we will display the contents of shirt underscore sizes. When we execute these statements, you can find that shirt underscore sizes is a factor and the output displayed contains the elements in the factor, and the next statement displayed is the levels, which are unique values from within the factor. We can also use str function, passing shirts underscore sizes as the argument. The str function displays the structure of the object passed. When we execute the statement, you can find that shirt underscore sizes is a factor with 5 levels, as well as it displays the indexes of those levels. We can also use summary function, passing shirt underscore sizes as the argument. The summary function returns a table which comprises of the levels as well as the values or counts corresponding to those levels occurring within the factor. So if you observe, the level L occurs twice in the vector. In the same way, level m occurs thrice in the vector. In the same way, the level s occurs twice, as well as xl also occurs twice, and even xxl occurs twice. Our programming language also provides levels as a function, which takes an object as an argument. In this case, let us provide the argument as shirts. When we execute the statement, you can find that we have the output as null, because level function works on factors, not on vectors. In this case, shirts is a vector and not a factor. Let us provide shirt underscore sizes as an argument to the levels function. When we execute the statement, you can find that all the levels of the factor, that is shirt underscore sizes, are displayed. We can also use table function passing factor as an argument. In this case, it will be shirt underscore sizes. When we execute the statement, you can find that table is displayed where the first row contains the levels and the second row displays the count of the elements corresponding to that level within the vector. In this video, we will look at how to visualize qualitative data. We can use bar plots. A bar plot is used to display the relationship between numeric and a categorical variable. Pie charts. A pie chart is a circular statistical graphics which is divided into slices to illustrate numerical proportions of categorical data. We will use the example of shirt sizes as qualitative data. Let us create an object shirts, and using the assignment operator and C function, we will assign values to the shirts vector. In the next statement, we will create an object shirt sizes, and using assignment operator and factor function, we will create shirt sizes as factor. In this case, we will pass the shirts as the argument for the factor function. We will create another object, that is shirts table, and using the assignment operator, we will use tables function and pass shirt sizes as the argument. In the next statement, we will display the content of the shirts table. Let us execute these statements. You can find that a table is displayed where first row is levels and the second row is count of elements corresponding to the levels in the vector. Let us now visualize the qualitative data by creating bar plot. We will use bar plot function and pass shirts table as the argument. When we execute the statement, you can find that bar plot is created, where levels are displayed on x-axis and y-axis represents the count from the table. We can customize this bar plot by assigning colors to different bars using the COL parameter and assigning the colors using the C function. Let us assign the colors as blue, green, red, yellow, and black. We will also use ylab parameter and assign the label as count. When we execute this statement, you can find that we have customized bar plot with label on y-axis and bars represented through different colors. Suppose if we have to find the count of various levels without displaying the graph, for example, I want to find how many shirts are of medium size. Let us use the statement shirt sizes equals m, where m stands for medium size. When we execute the statement, we get the result as a logical vector. The values true are displayed where the value m is found in the vector. We will now use sum function and will pass shirt underscore sizes equals m. When we execute the statement, we get the result as 4. In the same way, we can count how many shirts of XXL size are present. We get the result as 2. When we are using bar plot, we need to pass the argument as a table. We can also use plot function which takes in the factors as an argument. Plot is a generic function which displays the graphical summary of the factors. When we execute the statement, we get the basic bar graph, which is same as generated through bar plot function. We can also customize the graph using the COL and ylab parameter of the plot function. Let us use COL parameter and assign the values as blue, green, red, yellow, and black. as well as we will assign count as the label to ylab parameter. We can also create pie chart, which is a circular statistical graphics. We will use pie function and pass the argument as the table, in this case shirts table. When we execute the statement, we get the basic pie chart displayed, which shows the illustrations of numerical portions of the categorical data. We can customize the pie chart by using the COL parameter. When we execute the statement, we get the pie chart displayed in different colors. Let us consider another example. We will create a vector as age and assign various values and convert this into a factor. In the next statement, we will use table function and pass age as the argument. When we execute the statement, we get the result as table displayed. In the next statement, we will use level function and pass the argument as age. When we execute the statement, you can find that levels are displayed. In this case, you can find that there are 4 levels and assume that we have this qualitative data which represents group of ages. So let us use level function with the age as the argument, and using assignment operator, we will assign the vector. So we will use C function, and let us consider the first age group as less than 14, the next as 15 to 24, and the third as 25 to 34, and the last as greater than 35. We will now display the table function with the age as the argument. When we execute the statement, you can find that the levels now represent the labeled values. We can now use the bar plot function to graphically analyze the qualitative or categorical data. We can also customize the bar plots using the COL parameter and ylab parameter. When we execute the statement, we get the following result. We can also use the pie function to display the pie chart as well as customize the same using COL parameter. You can observe that the numerical portions of the categorical data is now displayed with the values assigned to the levels function, which displays the group of ages. So this is how we can visualize the qualitative data in R programming language. In this video, we will talk about how to handle quantitative data, that is, how to handle continuous or numerical data. Quantitative data can be counted, measured, and expressed using numbers, whereas qualitative data is descriptive and conceptual. Contrary to qualitative data, quantitative data is statistical and is typically structured in nature. This type of data is measured using numbers and values, which makes it more suitable for data analysis. The qualitative data is open for exploration, whereas quantitative data is much more concise. Quantitative data will almost always be considered structured data. This type of data is formatted in a way so it can be quickly organized and searchable within relational databases. Perhaps the most common example of structured data is numbers and values found in spreadsheets and is generally preferred for data analysis. The quantitative data can be obtained from experiments or measurements, or the best example of quantitative data is company stock price. Let us practically look at how to handle quantitative data in R programming language. Let us create an object songs, and using the assignment operator and the C function, let us provide the data values as 5.3, 3.6, 5.5, 4.7, 6.7, 4.3, 4.3, 8.9, 5.1, 5.8, and 4.4. Let us consider that these data items are the length of the songs, that is, the length of the song in minutes. In the next statement, we will display the value stored in the vector songs. Let us execute these statements. You can see that songs is created as a vector with all the elements as numeric. Let us consider another example for quantitative data. Let us create an object ratings And using the assignment operator and C function, we will provide the ratings as 2, 4, 3, 3, 2, 1, 1, 2, 3, 4, so on, so forth. Till 2, 4. In the next statement, we will display the values stored in the vector ratings. When we execute these statements, you can find that we have ratings as a numeric vector. So these two objects, that is songs and ratings, are now storing quantitative data, which is represented in numerics. In this video, we will look at how to visualize quantitative data. We can use histograms, which is a bar graph of raw data that creates a picture of the data distribution. The histogram represents the frequency of occurrence by a class of data. A histogram shows basic information about the data set. We can also use box plots, which is a standardized way of displaying the distribution of the data based on a summary, that is, minimum, first quartile, median, third quartile, and maximum. It also displays the outliers. As well as we can use strip chart, which produces one-dimension scattered plots or dot plots of a given data. These plots are a good alternative to box plots when sample size is small. Let us now practically look at how to visualize quantitative data. We will use an example of ratings as quantitative data. Let us create an object ratings, and using the assignment operator and C function, we will assign values to the ratings vector. Let us consider that the elements of the ratings vector represents the reviews or ratings of product given by different users. In the next statement, we will use length function and pass the argument as the vector, which is ratings in this case. This length function returns the number of items or elements in the ratings vector. In the next statement, we will use summary function, which is a generic function producing the summary results for the sample by passing the argument as a vector. In this case, it is ratings. Let us execute these statements. You can find that the length of the ratings vector is 22, and the summary result is displayed for the ratings sample, which displays the minimum, maximum, median, mean, and first and third quartiles. We will now visualize the quantitative data using the hist function, which computes the histogram for the given sample, that is ratings. The argument we will pass is the ratings vector. Let us execute these statements. You can find that histogram is displayed, which has ratings on the x-axis and frequency on the y-axis. We can also customize the histogram by using the COL parameter and assigning the value as blue. When we execute this statement, you can find that the bars of the histogram are in blue color. We can also compute the probability density by using the PROB parameter and assigning the value as true. When we execute this statement, you can find that histogram is displayed, which has ratings on the x-axis and density on the y-axis instead of frequency. We will now plot the histogram for frequency as well as the probability density function on the same graphical layout. To do this, we will use hist function to display the frequency histogram, and in the next statement, we will use the line function, passing the first argument as a density function with ratings and the second argument, which is COL parameter, assigning the value as red. When we execute these statements, you can find that histogram is plotted for frequency and the red line displays the values computed for probability density function. We will now plot the probability density histogram by using the probability parameter and assigning the value as true. When we execute these statements, we get the bars of the histogram and red line displaying the computed density function. We can also visualize the quantitative data using the box plots. To do this, we will use boxplot and pass the argument as ratings, which is a vector. When we execute this statement, we get the boxplot displayed, which consists of minimum, maximum, median, and first and third quartiles for the ratings data. We can also use plot function passing the ratings vector as an argument. When we execute the statement, we get the plot. We will also display the strip chart, which produces one-dimensional scatter plots. The argument we pass is the ratings vector. When we execute the statement, you can find that the strip chart is displayed. We can also customize the strip chart by using the COL parameter, and let us assign the value as red. As well as we can use the PCH parameter, which denotes the parsable character, and in this case we will assign the value as 15. When we execute the statement, you can find that the points are displayed as a block in red. When we use the strip chart function, the values of the ratings vector are overlaid on one another. Let us use the method parameter of the strip chart function and assign the value as jitter. When we execute the statement, we get the strip chart displayed with the data points as jittered. We can also assign stack as the value to the method parameter of the strip chart function. And when we execute the statement, we get the data points on the strip chart stacked. So these are the different ways through which we can visualize the quantitative data. Let us now practically visualize the real-time stock prices quantitative data. We will use GE stock price CSV dataset, where the first column is the date and the second column is the price on that date. We will use the library function to import the dplyr package. In the next statement, we will create an object as GE data, and using the assignment operator and the read.csv function, we will pass the argument as gestock.csv file. In the next statement, we will create GE price as an object, and using the assignment operator and select function from the dplyr package, we will pass the first argument as an object, that is in this case GE data, and the second argument as price, which is the name of the column in gestock.csv dataset. Let us execute these statements. In the next statement, we will use summary function, which is a generic function producing the summary results for the samples by passing the argument, in this case it is GE price. When we execute the statement, we get the summary statistics of GE stock data displaying the minimum, the max value, median, mean, first quartile, and the third quartile. We will now visualize the GE stock price quantitative data using the hist function, which computes the histogram for the given sample, that is in this case GE stock price. The argument we will pass is the price vector using the as.vector function. Let us execute these statements. You can find that histogram is displayed, which has price on the x-axis and frequency on the y-axis. We will also compute the probability density by using PROB parameter and assigning the value as true. When we execute the statement, you can find that histogram is displayed, which has ratings on the x-axis and density on the y-axis instead of frequency. We can also use COL parameter of the hist function and assign the value as blue. When we execute the statement, we get the customized histogram for the GE stock price data. We will now plot the histogram for density as well as the probability density function on the same graphical layout. To do this, we will use the hist function to display the density histogram. And in the next statement, we will use the line function, passing the first argument as a density function and second argument, which is COL parameter, assigning the value as red. When we execute these statements, you can find that histogram is plotted for density and the red line displays the values computed for a probability density function. If you observe, you can find that the line displayed for probability density function is out of the plot. We will use the y-limit parameter, that is YLIM, which is used for y-axis limit, and assign the value as a vector using the C function and passing the values as 0 and 0.025. When we execute these statements, we get the bars of the histogram plotted with blue color and the red line displaying the computed density function. In this video, we will look at different R functions that can be applied on quantitative data. Let us consider the same vectors, that is songs and ratings, which are storing the quantitative values. R provides a function, length, which takes in one parameter, that is the object. In this case, it is songs. This function will return the number of elements present in a vector. When we execute the statement, you can find that we have the length of the songs vector as 11. That means 11 data items are stored in the vector songs. Let us apply the same length function to the ratings vector. When we execute the statement, you can find that the length of ratings vector is 22. R provides a max function through which we can find the largest element in a vector. This max function will also take one parameter, that is the vector. In this case, it is songs. When we execute the statement, you can find that we get the result as 8.9, which is the largest element in the vector songs. In the same way, we will find the maximum element in ratings vector. We get the result as 4. We can also use min function, which operates on vectors to find the smallest element. In this case, min of songs will return us 3.6. R also provides a function sum, which gives the total of the elements in the vector. For example, sum of the vector songs will give the result as 58.6. PROD function gives the product of the elements in a vector. In this case, PROD of songs will give the result as shown in the output. The elements of the vector can also be sorted in increasing or decreasing order using the sort function. So for example, sort of vector songs will give us the vector songs in a sorted order. We can also sort the vectors in descending order using the decreasing parameter and assigning the value as true. Executing the statement, you can find that the songs vector is sorted in descending order. In this video, we will look at how to compute mean in R programming language as well as the different types of means. Mean is one of the measures of central tendency. There are three types of means, such as arithmetic mean, sometimes also called as just mean, geometric mean, and harmonic mean. The arithmetic mean of a sample is the sum of all values divided by the sample size. Here is the mathematical formula to compute arithmetic mean, where n is the sample size or number of items or elements in the sample, and this is the summation symbol. Here xi is the ith element of the sample, where I starts from 1 to n. Let us look at a simple example. Here we have sample x with the following elements. Each element is represented as x1, x2 till x8. Here the sample size is 8, that is, in this case n is 8, which is the number of elements in the sample. Now the summation of elements of the sample from I1 to n, or in this case from I1 to 8, is 30. So now the mean is sum of all the values, which is 30, divided by the number of elements in the sample, which is 8. So we have 30 divided by 8, which is 3.75. Let us now look at how to practically compute arithmetic mean in R programming language. Let us create an object songs, which is a vector. This vector contains some elements. In the next statement, we will display the values stored in the object songs. Let us execute these statements. We will now create an object M which will store the value for mean computed. With the assignment operator, we will use sum function, passing the argument as songs in this case. The sum function returns the sum of all the elements in the vector songs. We will then use the divide operator and divide the sum by the length of the vector songs using the length function. The length function returns the length of the vector or number of elements in the vector. In the next statement, we will display the value stored in an object M. When we execute these statements, we get the value of the mean. Let us consider, for example, that the vector songs contains the length in minutes of different songs. To answer a question that what is the average time I need to spend to listen to a song, then mean is used to answer this question. And here is the answer. I need an average of 5.327 minutes to listen to a song. R also provides statistical functions such as mean, which computes the mean of the elements in the vector. And this is same as sum of x divided by length of x. When we execute the statement, we get the same result. Let us now talk about geometric mean. The geometric mean is defined as the nth root of the product of all data. Here is the mathematical formula to compute geometric mean, where n is the sample size or number of items or element in the sample, and this is the mathematical product function. Here xi is the ith element of the sample, where I starts from 1 to n. Let us look at a simple example. Here we have sample x with the following elements. Each element is represented as x1, x2 till x8. Here the sample size is 8, that is, in this case n is 8, which is the number of elements in the sample. Now the product of the elements of sample from I equal to 1 to n, or in this case I equal to 1 to 8, is 11520. So now the geometric mean is the nth root, that is, in this case 8th root of the product of all the values, which is 8th root of 11520. And the answer is 3.2187. Let us now look at how to practically compute geometric mean in our programming language. Let us create an object songs which is a vector. This vector contains some elements. In the next statement, we will display the value stored in object songs. We will now create an object gm which will store the value of geometric mean computed. With the assignment operator, we will use the prod function, passing the argument as songs in this case. The prod function returns the product of all the elements in the vector songs. We will then use the exponent operator and compute the power of 1 divided by the length of the vector songs using the length function. The length function returns the length of the vector. In the next statement, we will display the value stored in an object gm. When we execute these statements, we get the value of geometric mean. The computation of geometric mean using the prod function is not efficient since the product of all the elements of the vector may result in a very large value. Therefore, the efficient way to compute the geometric mean is to use the logarithm function. For example, we can use exp function which computes the exponential. The argument we will call is the mean function, and inside the mean function we will call log function, and the argument we will pass to the log function is the songs vector. The next statement we will display the value stored in gm object. When we execute these statements, you can find that the value of geometric mean is computed, which is the same as above. In this video, we will look at the applications of geometric mean. The geometric mean is most commonly applied and used in business and financial applications, such as calculating the growth rate or computing the returns on portfolio of securities. Let us take an example of growth rates. The growth rate calculations for stocks is sometimes also referred to as compounded annual growth rate. Let us consider a stock of a company which grows by 10% in the first year. Assume that we have $100 invested, so growing by 10% will give the result as 100 plus 10, that is, the value of stock is 110. The same stock in the second year declines by 20%. So now we have 100 minus 20, which is 20%, and will give us the result as 80. And let us assume that in the third year, the stock grows by 30%. So we have 100 plus 30, which is equal to 130. We can use the geometric mean to compute the compounded annual growth rate. So therefore, the growth rate will be cube root of the product of 110, 80 and 130. If you consider in this case, our vector contains three elements, that is 110, 80 and 130. The length of the vector is 3. Therefore, computing the geometric mean, we get the result as 104.586. Now since we are computing the annual growth rate in terms of percentage, so the value 104.586 minus 100 will give us 4.586%. Now we can say that the annual compounded growth rate of the stock is 4.586%. Let us practically see how the growth rate can be computed in our programming language. Let us consider a vector stock. Using the assignment statement and C function, we will have three elements. The first element of the vector will be 100 plus 10. The second element is 100 minus 20, and the third element is 100 plus 30. So now we have the vector as 110, 80 and 130. In the next statement, we will create an object gmean to compute the geometric mean. Using the assignment statement and product function, we will pass stock as the argument for the product function, followed by the exponential operator, and then within parentheses, we will have 1 divided by length of the stock's vector. In the next statement, we will display the value stored in gmean's object. When we execute these statements, you can find that we get the result as 104.586. Since the annual growth rate is represented in terms of percentage, we will have a statement gmeans minus 100, and when we execute the statement, we get the result as 4.586%. So we can say that the stock has grown 4.586% over 3 years. So this is how geometric mean can be used to compute annual growth rate of stocks. Let us now talk about the harmonic mean. The harmonic mean is the reciprocal of the mean of the reciprocals of a sample. Here is the mathematical formula to compute harmonic mean, where n is the sample size or number of items or element in the sample, and this is the mathematical summation symbol. Here xi is the ith element of the sample, where I starts from 1 to n. The result of the mathematical summation when divided by n is again divided by 1 to get the harmonic mean. The condition which needs to be taken care in this equation is that the value of xi should always be greater than 0. If it is 0, then 1 divided by 0, that is the value of xi, will result in undefined or infinite value, and the harmonic mean cannot be computed. Let us look at a simple example. Here we have sample x with the following elements. Each element is represented as x1, x2 till x8. Here the sample size is 8. Now each element of the sample will be 1 divided by the value of the element. Then the summation is computed. We get the result as 2.991. So now the result is sum of all the values, which is 2.991, divided by the number of elements in the sample, which is 8. So we have 2.991 divided by 8, which is 0.374. So the harmonic mean is 1 divided by this value, of 0.374, which gives the result as 2.674. Let us now look at how to practically compute harmonic mean in R programming language. So now the harmonic mean is 1 divided by mean of 1 divided by songs. Remember that the songs is a vector. So 1 divided by songs will actually be computed as 1 divided by each element, and then the mean is calculated. In the next statement, we will display the value stored in an object hm. When we execute these statements, we get the value of the harmonic mean, which is 5.0377. Let us compare the values of all the means computed. We will use the mean function and pass the argument as songs. Let us execute these statements. You can find that the arithmetic mean of the sample songs is 5.2372. The value of geometric mean is 5.1716, and the value of harmonic mean is 5.0377. So this is how we can compute a mean, that is arithmetic mean, geometric mean, and harmonic mean in R programming language. The harmonic mean helps to find multiplicative or divisor relationship between fractions without worrying about common denominators. The harmonic mean are often used in averaging, like rates. For example, the average travel speed during different trips. The harmonic mean is also used in finance to average multiples, like the price-earning ratio and other financial calculations. In this video, we will look at other measures of central tendency, that is, median and mode. Median is one of the measures of central tendency. Median is the middle number in a sorted list of numbers. To determine the median value in a sequence of numbers, the numbers must be sorted, or arranged in a value order from lowest to highest or highest to lowest. The median can be used to determine an approximate average or mean, but it is not to be confused with the actual mean. If there are odd elements, the median value is the number that is in the middle, with the same amount of numbers below and above or to the right and left. If there are even elements in the list, the middle pair must be determined, added together and divided by 2 to find the median value. The median is sometimes used as opposed to mean when they are outliers. The outliers in the sequence might skew the average of the values. The median of a sequence can be less affected by outliers than mean. Let us consider a simple example of number of elements. Here we have 7 elements. We need to sort these elements in ascending or descending order. After sorting the elements, we will find the middle value. That is, in this case it is 4. So here median is 4. Let us consider another example. After sorting the n elements, we get 2 middle values. That is, in this case 3 and 4. So median in this case will be 3 plus 4, that is 7 divided by 2, and the result is 3.5. Let us now look at another measure of central tendency, that is mode. The mode is the number that appears most frequently in a set. A set of numbers may have one mode, more than one mode, or no mode at all. The mode can be the same value as the mean or median, but this is not always the case. For normal distribution, the mode is also the same value as the mean and the median. Let us consider a simple example. In this case, we have sample of elements. If you observe, the element 2 occurs most number of times. So therefore, the mode of this sample is 2. Let us consider another sample. In this case, we have the element 2 occurring twice, as well as element 4 also occurs twice. So therefore, here we have 2 modes, that is element 2 and element 4. Let us consider another example. In this sample of elements, none of the elements occur more than once. In this case, this sample has no mode. Let us now look at how to practically compute median in R programming language. We will use an example of songs as quantitative data. Let us create an object songs, and using the assignment operator and C function, we will assign values to the songs vector. The elements of the songs vector represent the length of each song or duration of each song in minutes. In the next statement, we will use mean function and pass the argument as a vector songs. This statement will compute the arithmetic means of songs vector. In the next statement, we will use median function, which computes the median for the vector by passing the argument as songs in this case. Let us execute these statements. You can find that mean for the vector song is computed, which is 5.327, and the median for the vector songs is computed, which is 5.1. Let us look at another example. We will create a vector for ratings of the product. In the same way, we will use the mean function by passing ratings vector as an argument. In the next statement, we will use the median function by passing ratings as the argument. Let us execute these statements. You can find that mean for the vector ratings is computed, which is 2.59, and the median for the ratings vector is computed, which is 3. So this is how mean and median is computed in our programming language. There is no function defined to compute mode as a measure of central tendency, because mode is not useful for statistical analysis. Do remember that mode is a function defined in our programming language, but this mode function returns the type of storage mode of an object and does not compute the mode for statistical analysis. In this video, we will talk about outliers. Outliers are highly deviated data values. These data values extremely affect the data analysis. Let us now practically look at outliers. We will use an example of salary as quantitative data. Let us create an object salary, and using the assignment operator and C function, we will assign values to the salary vector. Let us consider that the elements of the salary vector represent the yearly salary in thousands of the employees in an organization. In the next statement, we will display the elements stored in the salary vector. We will use mean function and pass the argument as the vector, which is salary in this case. This mean function computes the arithmetic mean of salaries of employees. In the next statement, we will use median function, which computes the median for the vector by passing the argument as a vector. In this case, it is salary. Let us execute these statements. You can find that mean salary is 16.667 and median for salaries is 17. Now, if you observe here in this case, there is no much difference between the mean and the median computed. Let us also consider the salary of the president of the company. Let us say that he is highly paid, so the value will be 90,000. We will execute these statements once more. You can find that now the mean salary is 27.142 and the median is 18. You can observe that there is very high difference between the mean and the median. This is because of the result is strongly influenced by the outlier, which is in this case the value 90, that is the salary of the president of the company. And observing the result, it is very wrong to estimate that the average salary of the employees is 27.142, since the salaries of all the employees except the president is way below the mean. Let us graphically analyze the results. We will use the boxplot function and pass the argument as salary. We will execute the statement. You can observe that the boxplot function displays the median. And we can also observe the outlier, which is displayed as a small circle. Let us remove the outlier from the vector and execute the statement. You can observe that the boxplot displays the median, whereas there are no outliers. We will include the outlier, that is in this case the value 90. In the boxplot function, we will use the range parameter and assign the value as 0. When we execute these statements, you can find that the extreme data points, that is the outliers, are also included in the box plot. Let us again use the mean function, passing salary as an argument. The mean function also has trim as a parameter. We will assign the value as 0.1. When trim parameter is used, the fraction of the observations are trimmed from each end of the vector. In this case, we are trimming with a fraction of 0.1. When we execute the statement, you can find that we have the trimmed mean, which is same as the above, that is 27.142. When the fraction of the trim parameter is used as 0.5, we get the same result as median. When we change the fraction of the trim parameter to 0.2, we get the result as 17.6, which is much better than the untrimmed mean, since 0.2 fraction of the observations are trimmed, and in this case the influence of the outlier is negligible. In this video, we have seen how outliers affect or have influence on the measure of central tendency, that is mean and median. Do remember that fraction of trim parameter of the mean function lies between 0 to 0.5. In this video, we will talk about quartiles and quantiles, which is another measure of statistics. A quartile is a statistical term describing a division of observations into 4 different intervals, based upon the value of the data and how they compare to the entire set of observations. To understand the quartile, it is important to understand the median as a measure of central tendency. The median in statistics is a middle value of a set of numbers. It is the point at which exactly half of the data lies below and above the central value. The quartile measures the spread of values above and below the mean by dividing the distribution into 4 groups. The quartile divides data into 3 points, a lower quartile, median, and upper quartile, to form 4 groups of the data set. Quartiles are used to calculate the interquartile range, which is a measure of variability around the median. The median is a robust estimator of location, but says nothing about how the data on either side of its value is spread or dispersed. This is where quartiles are used. The quartiles measure the spread of values above and below the mean by dividing the distribution into 4 groups. Each quartile contains 25% of total observations. Generally, the data is arranged from smallest to largest. The first quartile represents the lowest to 25% of numbers. The second quartile lies between 25.1% to 50%. That is up to the median. The third quartile lies between 51% to 75% above the median. And the fourth quartile is the highest 25% of the numbers. Let us look at an example of a sample data to compute the quartiles. We have 7 elements in a sample data set. This data set is sorted and the first element will be of minimum value, and the last element will be the maximum value. The middle element is the median. The values below the median and the minimum value are used to compute the first quartile, which is in this case the average of 2 numbers, and the result is 2.5. The values above the median and the maximum value are used to compute the third quartile, which is in this case the average of 2 numbers, which is 5.5. Let us now practically look at quartiles. We will use an example of songs as quantitative data. Let us create an object songs, and using the assignment operator and C function, we will assign values to the songs vector. Let us consider that elements of the songs vector represents duration or length of the songs in minutes. In the next statement, we will use mean function and pass the argument as vector, which is songs in this case. This mean function computes the arithmetic mean of duration of songs. In the next statement, we will use median function, which computes the median of the vector by passing the argument as a vector. In this case, it is songs. We will use summary function and pass the argument as songs. The summary function is a generic function which displays the summary of the quantitative data. Let us execute these statements. You can find that mean is computed, which is 5.327, and median is 5.1. The summary function displays the brief summary of data, that is minimum value, maximum value, median, mean, first quartile, and the third quartile. We also have a function quantile which produces quantiles corresponding to the given probabilities. The first argument is the vector, that is songs in this case, and the second argument is the probabilities, that is in this case we will have 0.25 and 0.75. When we execute the statement, we will get the values for 25% and 75% quantiles. In this video, we have seen how quartiles and quantiles are computed. Do remember that the probabilities of quantiles lies between 0 to 1 in the quantile function. In this video, we will talk about variance and standard deviation, which are the measures of variation and spread. The measures of variation are used to measure variability in the data or to qualify the accuracy of statistical parameters. The most common measure of variation is the variance and its square root, that is, the standard deviation. Variance in statistics is a measurement of the spread between numbers in a data set. That is, it measures how far each number in the data set is from the mean, and therefore from every other member in the set. The standard deviation is a statistic that measures the dispersion of the data set relative to its mean and is calculated as the square root of the variance. The standard deviation is a statistical measure in finance that, when applied to the annual rate of return of an investment, sheds light on the historical volatility of that investment. The greater the standard deviation of securities, the greater the variance between each price and the mean. For example, a volatile stock has the high standard deviation, while the deviation of a stable stock is usually rather low. The variance is calculated by first finding the deviation of each element in the data set from the mean, and then by squaring it. Finally, dividing the result by the degree of freedom, which is the sample size minus 1. This is the mathematical equation for computing the variance, where xi is the ith element in the dataset or the sample, and x dash is the mean of the dataset or sample, and n-1 is the degree of freedom, which is the sample size minus 1. Let us now practically look at how to calculate variance and standard deviation. We will use an example of songs as quantitative data. Let us create an object songs, and using the assignment operator and C function, we will assign values to the songs vector. Let us consider that the elements of the songs vector represent the duration or length of the song in minutes. In the next statement, we will use var function and pass the argument as the vector, which is songs in this case. This var function computes the variance of the duration of songs. In the next statement, we will use SD function, which computes the standard deviation for the sample by passing the argument as the vector. In this case, it is songs. Let us execute these statements. You can find that variance is computed, which is 2.1301, and the standard deviation is 1.4595. We will take another example. This time we will be using ratings as the quantitative data. Let us create an object ratings, and using the assignment operator and C function, we will assign the values to the ratings vector. Let us consider that the elements of the rating vector represent the ratings of a product given by the different users. In the next statement, we will use var function and pass the argument as the vector, which is ratings in this case. This var function computes the variance of ratings. In the next statement, we will use SD function, which computes the standard deviation for the sample by passing the arguments as a vector. In this case, it is ratings. Let us execute these statements. You can find that variance is computed, which is 1.1103, and the standard deviation is 1.0537. If you observe the variances computed for songs and for ratings, the variance for songs is more than the ratings. And this means that there is a large variation between the songs data sample when compared to the ratings data sample. The same difference can be observed in standard deviation for both the samples. Let us now look at an example of real-time stock prices. We will use the dplyr package by importing the dplyr library using the library function and passing dplyr as the argument. In the next statement, we will create GE data as an object, and using the assignment operator and read.csv function, we will fetch the stock price data of GE stock by passing the gestock.csv file name. If we view the gestock.csv file, you can find that it consists of date and stock price on that date. In the next statement, we will create an object GEPrice, and using the assignment statement and select function, we will read the price data by passing the first argument as GE data and the second argument as price, which is the second column in the data set. In the same way, we will create an object IBM data, and using the read.csv function, we will read the data from the IBM stock.csv file. In the next statement, we will have IBM price object, and using the select function, we will pass the first argument as IBM data and the second argument will be the price column. Before we execute these statements, let us set the working directory to the directory where we have the above CSV files. Let us execute these statements. We will use the var function, which returns the variance, passing GEPrice as an argument, as well as in the next statement we will call the var function and pass the IBM price as an argument. Let us execute these statements. You can find that the variance for GE stock price is 575.6425 and the variance for IBM stock price is 7712.717. The greater the variance for stock price, the greater volatility of the stock. So here IBM stock price is more volatile than the GE stock price. In the same way, we will compute the standard deviation for GE and IBM stock price using the SD function. The argument that needs to be passed to the SD function is a vector. And in this case, the GE price and IBM price are the data frames. Therefore, we need to convert the data frame to vectors using the as.vector function. When we execute these statements, we get the standard deviation for GE stock price, that is 23.9925. And for the IBM stock price, we get the result as 87.8220. Here also you can observe that there is a huge difference in the standard deviation for both the stock prices, and IBM stock price is more volatile than the GE stock price. In this video, we will talk about correlation and covariance. Correlation in finance and investment industries is a statistic that measures the degree to which two securities or stock price move in relation to each other. In finance, the correlation can measure the movement of a stock with that of a benchmark. Correlation measures association, but does not tell us which factors affect the correlation among stock prices. The correlation is computed using this mathematical formula, where R is the correlation coefficient and X dash and Y dash are the means of the two observations. The result of correlation coefficient can be positive or negative, but the value will always be between minus 1.0 and plus 1.0. A positive correlation means stock prices move in the same direction. When the correlation coefficient is 1, it is a perfect positive correlation. This implies that as one security moves or the stock price moves either up or down, the other security or stock price moves in the same direction. A negative correlation means the stock prices moves in the opposite direction. A perfect negative correlation is that the two assets or stock prices moves in opposite directions. While a zero correlation implies no relationship exists at all between the stock prices. Let us now practically look at how to compute correlation and covariance. To have better understanding of the concepts of correlation, we will use sample vector to perform correlation. Let us create an object X and assign some elements. Let's say the elements are 10, 20, 30, 40 and 50. We will also create another object Y. Let's say that we are assigning the same elements. We will now use the COR function, which computes the correlation between the two samples, that is, in this case, sample X and sample Y, or vector X and vector Y. We will pass the arguments as vectors, in this case X and Y, to the COR function. When we execute these statements, you can find that the correlation of sample X and sample Y is 1. This is because the elements are same in both the samples, so there is a perfect positive correlation. Let us look at another scenario. Let's assume that we have the elements of Y sample as 50, 40, 30, 20 and 10. When we execute these statements, you can find that the correlation is minus 1. This is because the elements in sample X and sample Y are exactly reverse. So there is a perfect negative correlation. Let us now assign some arbitrary elements to the sample, or in this case vector X as well as vector Y or sample Y. We will use the same COR function, that is the correlation function, to compute correlation between two samples. When we execute these statements, we get the correlation as 0.6481. We can observe that there is a positive correlation between the samples. Let us consider another example. We will use another set of elements in sample Y. When we execute these statements, we get the correlation as minus 0.4799. We can observe that there is a negative correlation between these samples. We will now find the correlation between the stock prices. We will use the GE and IBM stock prices dataset. This dataset contains two columns. The first column represents the date, and the second column represents the price of the GE stock on that date. Let us import the dplyr package using the library function and passing dplyr as the argument. In the next statement, let us create an object myGEData, and using the assignment operator and read.csv function, we will pass the argument as gestock.csv file. In the next statement, we will create GEDates as the object, and using the assignment operator and select function, we will pass myGEData as the first argument and date as the second argument, which is the column name in the data set. In the next statement, we will create another object, that is GE price, and using the assignment operator and select function, we will pass myGEData as the first argument and price as the second argument, which is the column name in the data set. In the next statement, we will read IBM stock price data. So let us create an object myIBMData, and using the assignment operator and read.csv function, we will pass the argument as IBM stock.csv file. In the next statement, we will create IBM dates as the object, and using the assignment operator and select function, we will pass myIBMData as the first argument and date as the second argument, which is the column name in the data set. In the next statement, we will create another object, that is IBM price, and using the assignment operator and select function, we will pass myIBMData as the first argument and price as the second argument, which is the column name in the data set. Before we execute these statements, we will set the working directory to the directory where we have the CSV files. Let us execute these statements. We will now use the COR function, which computes the correlation between two stock prices. In this case, the first argument we will pass is the GE price, and the second argument we will pass is the IBM price. When we execute the statement, you can find that correlation is computed between stock prices of GE and IBM, and the value is 0.1098. If the dataset of the arguments we pass to the correlation function contains null values or NA values, then the correlation function will not work. Since the dataset may be very large, therefore we can have use parameter and assign the value as complete.obs to compute correlation with NA values in the dataset. When we execute the statement, you can find that we get the same correlation result, since our dataset of stock prices does not contain any null or NA values. There are different ways of computing correlation. We can use the method parameter and assign the value as Spearman. When we execute the statement, you can find that we get the value as 0.1665, which is different from the earlier correlation value. This is because by default the correlation function uses Pearson's correlation. Using our programming language, we can also compute correlation test using different methods. Since correlation tests are performed on vectors, we will create a vector GE price vector, and using the as.vector function, we will pass the argument as GE price $price. We will also create another vector as IBM price vector, and using as.vector function, we will pass IBM price $price as the argument. We will now use the cor.test function, which computes the correlation test, passing the argument as GE price vector and the other argument as IBM price vector. We will also use the method parameter and assign the value as Pearson. That is the method to compute the correlation. When we execute these statements, you can find that results of Pearson's correlation test are displayed, where the p-value is 0.01607 and the correlation value is 0.1098. We can perform correlation test using Spearman method, and when we execute the statement, you can find that we get the correlation value as 0.1665. In the same way, we can perform the correlation test using the Kendall method, and we get the value as 0.1215. We will now talk about the covariance. Covariance is a statistical tool that is used to determine the relationship between the movement of two asset prices. When two stocks tend to move together, they are seen as having a positive covariance. When they move inversely, the covariance is negative. Covariance is a significant tool in modern portfolio theory, used to ascertain what securities to put in a portfolio. Covariance is calculated by analyzing return surprises, that is the standard deviation from the expected return, or by multiplying the correlation between the two variables or samples by the standard deviation of each sample or variable. In our programming language, the covariance is computed using the COV function. The first argument we will pass is the GE price, and the second argument we will pass is the IBM price. When we execute the statement, we will get the result of covariance, that is, in this case 231.4354. In this video, we will look at the correlation coefficients and covariance using different stock prices. We will first compare the correlation and covariance between GE and IBM stock prices. Here we have the same statements which we have seen in the previous video. Let us execute these statements. You can find that we have the correlation value of GE and IBM stock as 0.1098 and covariance between the same stocks as 231.435. We will now use the stock price of Coca-Cola Company, which also has date and price as the columns. In the read statement, instead of using the IBM dataset, we will use the Coca-Cola dataset. Let us not bother about the other objects which we have used, such as my IBM data, since these are just names which we have used and it doesn't matter. Let us execute these statements, which will now compute the correlation and covariance between GE and Coca-Cola stock prices. You can observe that now we have the result of correlation as 0.1775 and covariance as 107.2014. When we compare the correlation value of GE and IBM stock, we get the result as 0.1098, and between GE and Coca-Cola, we get the value as 0.1775, which is greater than the previous correlation value. Therefore, we can conclude that GE and Coca-Cola stock prices are comparatively more related than GE and IBM stock prices. In the same way, the covariance between GE and IBM data is 231.435, and whereas between GE and Coca-Cola is 107.2014, which is much lesser than the previous covariance value. Therefore, we can conclude that there is a large variation between GE and IBM stock prices when compared to GE and Coca-Cola stock prices. So this is how we can apply the concept of correlation and covariance on stock prices data or financial data. In this video, we will talk about the basic approaches of dealing with two variable data or bivariate qualitative data. A great deal of statistical analysis is based on describing the relationship between two data variables. For example, how are height and weight of humans related? Or how is the heart diseases different in men and women? Or we can also have a question to analyze how does planting of seeds alter crop yield? The bivariate data may consist of two qualitative variables, or one qualitative and one quantitative variable, or two quantitative variables. Let us now practically look at how to handle bivariate qualitative data. We will use an example of ratings data. Let us create an object ratings, and using the assignment operator and C function, we will assign values to the ratings vector. Let us consider that the elements of the ratings vector represent the reviews or ratings of a product given by different users. In the next statement, we will convert the ratings vector into ratings factor using the ratings object with the assignment operator and factor function by passing ratings as the argument. We will use another example of courses data. Let us create an object courses, and using the assignment operator and C function, we will assign values to the courses vector. Let us consider that the elements of the courses vector represents courses in terms of zeros and ones. In the next statement, we will convert the courses vector into courses factor using courses object with the assignment operator and factor function and by passing courses as the argument. Let us execute these statements. Let us now assign the names of the courses to the courses factor using the levels function. We will use the assignment operator, and using the C function, we will have first element as R and the second element as Python. So the value 0 in the courses vector is now represented by string R, and the value 1 in the courses vector is represented by string Python. In the next statement, we will use the table function, passing the first argument as ratings and the second argument as courses. The table function builds a contingency table of the counts at each combination of factor levels. In this case, the contingency table is built for the counts of ratings and courses combination. When we execute these statements, you can find that values of ratings factor represents the rows of the table, since rating is passed as the first argument, and the values of courses factor represent the columns of the table. The values of the tables represents the count of rating corresponding to the courses. Now suppose if we pass courses as the first argument and ratings as the second argument of the table function and execute this statement, you can find that courses are represented as rows and ratings are represented as columns. We will now use the bar plot function to visualize the bivariate qualitative data. For the bar plot function, the argument we will use is the table function, and for the table function, we will pass ratings and courses as the arguments. When we execute this statement, we get the bar plot where x-axis represents the courses and y-axis represents the count of the ratings. We will customize this bar plot function by using the COL parameter and assigning 4 values as a vector, such as blue, yellow, red, and green. When we execute this statement, you can find that the bar plot displays each rating with a different color. Suppose if we pass courses as the first argument and ratings as the second argument and execute this statement, we get the bar plot where ratings are represented on x-axis and courses are represented on y-axis, with each course displayed in different color. Here, even though we are passing 4 colors, the bar plot displays only 2 colors because the courses factor only contains 2 levels, that is zeros and ones, which is represented as a string of R course and Python course, respectively. We will use the legend.text parameter and assign the value as true. When we execute this statement, you can find that legend is displayed, which shows the color of each course. Now suppose if we pass the ratings and courses as the first and the second argument for the table function and execute this statement, you can find that now the legend displays the colors for the values of ratings factor. The bar plot function also provides the beside parameter, and if we assign the value as true and execute this statement, you can find that the bars are plotted side by side instead of the stacked bar plot. We will now look at another way of visualizing bivariate qualitative data. We will use mosaic plot function and pass the argument as a table function with ratings as the first argument and courses as the second argument. When we execute this statement, you can find that mosaic plot is displayed where x-axis represents the ratings and y-axis represents the courses. The length or height of the tile in mosaic plot depends on the value of the count of ratings. We can also customize the mosaic plot by using the COL parameter and assigning the value as a vector of colors such as blue and yellow. When we execute the statement, you can find that the tiles are displayed with yellow color for Python course and blue color for R course of the courses factor. So this is how we can handle the bivariate qualitative data in R programming language. In this video, we will practically look about the approaches of dealing with two-variable quantitative data or bivariate quantitative data. We will use GE stock prices dataset as the bivariate quantitative data. This dataset contains two columns. The first column represents the date and the second column represents the price of GE stock on that date. Let us import the dplyr package using the library function and passing dplyr as the argument. In the next statement, let us create an object GE data and using the assignment operator and read.csv function, we will pass the argument as gestock.csv file. In the next statement, we will create dates as the object and using the assignment operator and select function, and we will pass GE data as the first argument and date as the second argument, which is the column name in the data set. In the next statement, we will create another object for price and using the assignment operator and select function, we will pass GE data as the first argument and price as the second argument, which is the column name in the data set. We will visualize the bivariate quantitative data using the boxplot function. For the boxplot function, we will pass price object as the argument. When we execute these statements, we can find that a boxplot is created which displays the minimum price, maximum price, median price with the first quartile and third quartile as well as the outliers. The boxplot function only displays the values of the univariate data, that is, the data only about the price variable. We will use the plot function to display the line plot. The first argument we will pass is the price using GE data $price. The next argument we will pass is the value for the label of the x-axis using the xlab parameter and assigning the value as dates. The next argument we will pass is the value for the label of the y-axis using the ylab parameter and assigning the value as stock prices. The next argument we will pass is the COL parameter and assign the value as red to display the line in red color. The last argument we will use is the type parameter and assign the value as L, which represents line graph. When we execute this statement, you can find that a line graph is plotted where x-axis represents the dates and y-axis represents the stock price value corresponding to the respective dates. Although we can approximately find the max as well as the min value for the stock price from the visual plot created, but we can also use certain statements in our programming language to find the same. we will use the max function and pass the argument as GE $price. When we execute the statement, we can find that we have the maximum price of the GE stock traded. We will also use which function to get the index of the maximum value of the stock. In the which function, we will use GE $price followed by the equal to, which is a relational operator, and call the max function with GE $price as an argument. When we execute this statement, we get the result as 364, which is the index in the GE data object, that is the data frame. To retrieve the entire row belonging to the index, we will use GE data, which is the data frame, followed by the opening square brackets, and at the end of the statement, we will use comma to retrieve the entire row, followed by closing of the square brackets. When we execute the statement, you can find that we get the result as the max price of the GE stock, as well as the date on which the GE stock traded maximum price. In the same way, we can use the min function to find the minimum value of GE stock as well as its date. So this is how we can handle the bivariate quantitative data in R programming language. In this video, we will discuss about multivariate data. We have discussed the data frames in R and have seen how data can be imported. The data from the dataset may contain multiple variables that can be imported into a data frame, and this data frame can be used to work with multiple variables. In this video, rather than a full introduction to multivariate methods, we will cover some of the basic statistical analysis. Let us now practically look at how to perform analysis on multivariate data. We will consider the murders dataset, which consists of several variables. Most important is the population, murders, and gun murders. Let us import the dplyr package using the library function and passing dplyr as the argument. In the next statement, we will create an object myData, and using the assignment operator and read.csv function, we will pass the argument as murders.csv file. Let us display the contents of myData object. When we execute these statements, you can find that the entire content of murders.csv dataset file is stored in the myData object, which is a data frame. We will use the str function, which displays the structure of the contents of myData object. When we execute the statement, you can find that the dataset contains 25 observations and 8 variables. The state variable is a factor. The ABB variable is also a factor, as well as the region variable is also a factor. That is, they are qualitative variables. Let us use the summary function, which computes the basic summary of the data. When we execute the statement, you can find that summary results of state, ABB, and region variables are displayed. Since these variables are qualitative variables, the summary statistics is not useful. But whereas the summary statistics of population displays the computed minimum value, first quartile, median, mean, third quartile, and the maximum values. In the same way, you can find that the summary statistics of population density, murders, gun murders, and gun ownership are displayed. Let us now use the boxplot function and pass the argument as myData. When we execute the statement, you can find that boxplot for multivariate data is displayed. Here you can also observe that boxplot for qualitative as well as quantitative variables are displayed. In the same way, let us use the plot function to plot scattered plots, by passing myData object as an argument. When we execute this statement, you can find that matrix of scattered plots is displayed. Even here you can observe that the scattered plots for state, ABB and region is also displayed with other quantitative variables. The index of state, ABB and region variables is 1, 2 and 3 respectively. We will use pairs function, which also computes a matrix of scattered plots. We will pass the argument as myData, followed by the opening square bracket, and then followed by comma, since we need all the observations or rows of the data frame. And then for the columns, we will use negative sign with the C function. The indices we will pass are 1, 2 and 3. This means that include all the columns or variables except first, second and third indices. When we execute this statement, you can find that a matrix of scattered plots is displayed. You can observe that there is a close correlation between population and murders, as well as close correlation between murders and gun murders. Let us create another object, myDataSEL, and using the assignment operator and myData object, we will select all the quantitative variables from the dataset and leave out the qualitative variables such as state, ABB and region, which are on index 1, 2 and 3 respectively. We will even exclude the population variable, which is at index 4. We will use the bar plot function and pass the argument as myDataSEL. Let us execute these statements. You can find that we get an error. This is because the bar plot function cannot handle the data frame. The bar plot function works with matrix. And even though the data frame as well as matrix can be used to store multivariate data, but matrices and data frames are fundamentally different in our programming language. Therefore, we will convert the data frame into a matrix by using the data.matrix function and passing the argument as myDataSEL. Let us display the contents of the matrix, that is in this case my matrix. Let us execute these statements. You can find that matrix is displayed. But to use the content from this matrix, we need to transpose this matrix. Therefore, we will use the T function, which performs the transpose of a matrix, and pass the argument as myMatrix object. Now, instead of passing data frame as an argument, we will pass myMatrix as an argument. Let us execute these statements. You can find that the bar plot is displayed. We will customize this bar plot using the COL parameter and assigning 4 different colors. When we execute this statement, you can find that bars are displayed with respective colors. We will even exclude the population density variable, which is at index 5, and use only 3 colors. We will use the beside parameter and assign the value as true. When we execute the statement, you can find that the bars are plotted side by side. We will use names.arg parameter and assign the value as myData$state, which will display the labels for x-axis. We will also use legend.text parameter and assign the value as true. This will display the legend of the colors used in the bar plot. When we execute the statement, you can find that the bars are displayed side by side, with the labels on x-axis as well as the legend conveying which color is used to display values of which variables. If you observe, there is a relationship between murders and gun murders in all the states, as well as there are no bars displayed with green color. This is because the green color is used to display bars for gun ownership, whose values are very much smaller than the values compared to the murders and gun murders variables in the data set. So this is how we can perform basic statistical analysis on multivariate data. In this video, we will talk about probability distribution. A probability distribution is a statistical function that describes all the possible values and likelihood that a random variable can take within a given range. This range is within the minimum and maximum possible values, but precisely these possible values depends on a number of factors, which includes the distribution's mean, that is the average, standard deviation, and the skewness. Probability distribution is used in academics and financial analysis, as well as by fund managers and investors, to determine and evaluate possible expected returns that the stock price may yield in the future. There are many different classifications of probability distributions. Some of them include the normal distribution, uniform distribution, chi-square distribution, binomial distribution, and the Poisson's distribution. Different probability distributions serve different purposes and represents different data generation processes. The binomial distribution, for example, evaluates the probability of an event occurring several times over a given number of trials. A typical example would be to use a fair coin and figuring the probability that the coin comes up heads. A binomial distribution is discrete as opposed to continuous, since only 1 or 0 is the valid response. The most commonly used distribution is the normal distribution, which is used frequently in finance, investing, science, and engineering. Normal distribution is fully characterized by its mean and standard deviation, meaning the distribution is not skewed. This makes the distribution symmetric, and it is depicted as a bell-shaped curve when plotted. Stock returns are often assumed to be normally distributed, but in reality they exhibit kurtosis, with large positive and negative returns than would be predicted by a normal distribution. Probability distributions are often used in risk management as well as to evaluate the probability and amount of loss that an investment portfolio would occur based on a distribution of historical returns. Let us look at an example of a probability distribution. We will take a simple example of rolling two 6-sided dice. Each dice has a 1/6th probability of rolling a single number. So here are the possible outcomes we may get when rolling a two 6-sided dice. Here the sum of the two dices will form the probability distribution. The outcome of getting 2 when we roll the dices is 1, 1. So the probability of getting 2 is 1/36. In the same way, the outcome of getting 3 is 1, 2 or 2, 1. So the probability of getting an outcome 3 is 2/36. The outcome of getting 4 is 1, 3 or 2, 2 or 3, 1. And the probability is 3/36. And so on and so forth. And the sum of all the possible outcomes of rolling two dices is depicted here. If you observe, the outcome of getting 7 is the most common outcome, which has the probability of 6/36. And the probability of getting the outcome 2 and 12, on the other hand, is far less likely. That is, the probability is 1/36. Here we have the bar graph, which depicts the probability distribution of rolling two 6-sided dice. On the x-axis, you can find that we have the sum of two dices, and on the y-axis we have is the probability or the likelihood of getting the outcome. Let us look at an example of rolling dice in R programming language. We will create a vector dice total, and let us have all the possible results or outcomes we get by rolling 2 dice. We have the values of the outcomes as 2, 3, 4, 5, 6 till 12. We will also create a vector as possibilities, which corresponds to the possibilities of getting the outcome or total when 2 dices are rolled. We will now create a bar plot to understand the distribution. In the bar plot function, we will pass the possibility vector and use the COL parameter and assign the value as blue. We will also use the names.arg parameter and assign the vector, that is dice total. Let us execute these statements. You can find that the bar plot is created which displays the probability distribution of sum of rolling 2 dice. The probability distributions are one of the core concepts in statistics. We will now look at a random number generation on the computer system to get a feeling about randomness. The R programming language provides RUNIF function, which provides information about the uniform distribution. This function, when executed, returns random numbers. For example, we will use the RUNIF function and pass the argument as, let's say, 5. When we execute this statement, we get 5 random numbers uniformly generated. R in the function stands for random and UNIF stands for uniform distribution. You can observe that the numbers generated are decimal numbers, which lies between 0 to 1. The argument we have provided tells the function to generate those many numbers. We can also provide the minimum and maximum values such that the numbers are generated between the minimum and maximum range. For example, let us pass the argument as 5, 1, 6, where 5 is the numbers to be generated and 1 is the minimum value as well as 6 is the maximum value. Now suppose if we are interested in randomly generating the possibility of rolling a dice, we need to generate whole numbers rather than decimal numbers. To do this, we can convert the output generated by RUNIF function to integers using the as.integer function. For example, we can have as.integer around the RUNIF function. When we execute this statement, we get the simulation of rolling the dice 5 times and their outcomes. If we execute this statement again, you will get a different result or an outcome. In this video, we will talk about uniform distribution. In statistics, a type of probability distribution in which all outcomes are equally likely, that is, each variable has the same probability that it will be the outcome, is known as a uniform distribution. For example, a coin has a uniform distribution because the probability of getting either heads or tails in a toss is same. The coin flip returning a head or tail both have a probability of 0.5. Another example is a deck of cards. The likelihood or probability of drawing a heart, club, diamond or spade is equally likely. There are 2 types of uniform distribution: discrete uniform distribution and continuous uniform distribution. The possible result of rolling a dice provides an example of discrete uniform distribution. It is possible to roll any number from 1 to 6, but it is not possible to roll 2.5 or 4.8. Therefore, rolling a dice generates a discrete distribution with probability of 1 by 6th for each outcome. Some uniform distributions are continuous rather than discrete. An ideal random number generator would be considered a continuous uniform distribution. With this type of distribution, every variable has an equal opportunity of appearing. There are several other important continuous distributions, such as normal distribution, chi-square distribution, and student's t-distribution. A uniform distribution with only two possible outcomes is a special case of a binomial distribution. There are several data generating or data analyzing functions associated with distributions to help understand the variables and their variance within a data set. These functions include probability density functions and cumulative density functions. Let us look at how to generate uniform distribution in R programming language. Uniformly distributed random numbers have the same probability of occurrence in a given interval, that is between 0 to 1. In R programming language, random numbers are created with the function RUNIF, where R stands for random and UNIF stands for uniform. The argument we will pass is 10, which is how many random numbers are to be generated. When we execute this statement, you can find that 10 random numbers are generated. We will now create 200 random numbers and store them in an object X. In the next statement, we will use the hist function and pass the argument as a vector X. When we execute these statements, you can find that histogram is displayed, which shows the uniform distribution created with random numbers. Let us now look at an ideal case of theoretical uniform distribution. To find this, we need to compute the cumulative frequency, which can be displayed as a cumulative histogram. In the R programming language, the hist function cannot create cumulative plots, so we need to perform some computations. We will use hist function and pass the argument as object X, which contains 200 random numbers. The second argument we will pass is the plot parameter and assign the value as false. This is because we do not want to display the histogram. We only want to compute the histogram. We will store the computed histogram in an object H. Let us now display the value stored in object H. When we execute these statements, you can find that the structure of the histogram is displayed, which contains several attributes. We will make use of the count attribute and retrieve the result. We will use the cum/sum function, which returns a vector whose elements are cumulative sums. We will store the result returned in an object hcum. In the next statement, we will use the bar plot function and pass the argument as hcum. When we execute these statements, you can find that a bar plot is created, which displays the uniform distribution of the random numbers generated. In this video, we will talk about normal distribution. Normal distribution is a probability distribution that is symmetric about the mean, showing that the data near the mean is more frequent in occurrence than data far from the mean. The normal distribution is the most common type of distribution assumed in technical stock market analysis and in other types of statistical analysis. The normal distribution has two parameters, the mean and the standard deviation. Normal distribution is sometimes confused with symmetrical distribution. Symmetrical distribution is one where a dividing line produces two mirror images, in addition to a bell curve that indicates a normal distribution. In financial analysis, traders may plot price points over time to fit recent price action into a normal distribution. The further price action moves from the mean, in this case, the more likelihood that an asset is being over or undervalued. Investors or traders can use the standard deviations to suggest potential trades. This type of trading is generally done on very short time frames. Similarly, many statistical theories attempt to model asset price under the assumption that they follow a normal distribution. Please remember that even if the asset goes through a long period where it fits a normal distribution, there is no guarantee that the past performance truly informs the future prospects. Let us practically look at a normal distribution. The R programming language provides rnorm function to generate random numbers using normal distribution. We will use the rnorm function to generate 100 random numbers from normal distribution, with the mean as 50 and standard deviation as 10. Here the first argument is the number of random numbers, and the second argument, that is 50, is the mean, and 10, that is the third argument, is the standard deviation. In the next statement, we will use the hist function and pass the argument as x, the object which has 100 random numbers generated using normal distribution, and the second argument as probability and assign the value as true. This statement creates a histogram with values of probability density function. When we execute these statements, you can find that the histogram is plotted with density on y-axis. We will compute the mean using the mean function and pass the argument as x. We will also compute the standard deviation using SD function and pass the argument as x. When we execute these statements, you can find that the mean computed for 100 random numbers generated. We will now create a bell-shaped curve into the histogram. We will use the lines function and pass the argument as density function, with x as the argument. The second argument we will use is COL parameter and assign the value as blue. When we execute this statement, you can find that bell curve is displayed on the histogram. So this is how random numbers can be generated using normal distribution. In this video, we will talk about the significance of computing p-value for statistical hypothesis. Descriptive statistics can help us identify relationships in data. Descriptive statistics do not draw conclusions beyond the data samples. Inferential statistics does allow us to make conclusions beyond the data sample, that is the population. Inferential statistics is the process of drawing conclusions about the population based on a sample taken from the population. The sample is the data obtained from the population. The p-value is the probability that, if the null hypothesis is true, sampling variation would produce an estimate. The p-value tells us how likely it is to get a result like this if the null hypothesis is true. Let us consider a simple example. Let us say that Domino's sells pizzas at various locations all over the city. Assume that there is a complaint that the cheese on the pizza is not enough as it is supposed to be. Let's say that the Domino's has a policy that there would be 100 grams of cheese on every pizza. Obviously, the management can't visit all the shops in the city to check this complaint, so we can use the statistical test on the sample of pizzas. In this case, the null hypothesis is a thing we are trying to provide evidence against. The average or mean cheese in each pizza should be 100 grams. The alternative hypothesis is what we are trying to prove. That is, the customers have complained that the cheese on the pizzas is less than what it should be. So the alternate hypothesis is that the cheese on the pizzas is less than the average cheese, that is 100 grams. We will use the significance level as 0.05, which corresponds to the confidence level of 0.95, that is 95% confidence level. If the p-value is lower than the significance level, we can reject the null hypothesis. Let us practically look at how to compute p-values for statistical hypothesis. We will be using a dataset which consists of the amount of cheese on randomly selected pizzas. Let us import the dplyr package using the library function. In the next statement, we will create myData as an object, and using the assignment operator and read.csv function, we will read the data from Domino's cheese.csv file. In the next statement, we will display the content stored in myData object. When we execute these statements, you can find that the entire content from Domino's cheese.csv file is stored in myData object. In the next statement, we will have t.test function, which performs one or two sample t-tests on vectors of data. The first argument we will pass is myData object, which contains data from dominocheese.csv file. And the next argument we will pass is the mean. Using mu parameter, we will assign the value as 100. We are using this value as 100 because we have seen in the example that the policy is to have 100 grams of cheese on every pizza. Let us execute this statement. You can find that we have the p-value as 0.343 and the mean value is 98.7 for Domino's cheese data. Our significance level is 0.05, so therefore in this case p-value is greater than the significance value. So therefore we reject the null hypothesis and we will consider the alternate hypothesis. That is, we have proved that there is not enough cheese on the pizzas. So this is how p-value computation and comparing with the significance level helps in statistical hypothesis. In this video, we will discuss the degree of freedom. The degree of freedom refers to the maximum number of logically independent values, which are the values that have the freedom to vary in the data samples. The formula for degree of freedom equals the size of the data sample minus 1. Let us consider the same example of Domino's pizzas. In the first statement, we are importing the dplyr library. In the second statement, we are reading the data from Domino's cheese.csv file and storing in myData object. In the third statement, we display the contents of myData object. In the fourth statement, we use t.test function to perform t-test on the data. Let us execute these statements. You can find that when t-test is performed, we get the degree of freedom as 29. Let us have another statement. We will use the length function and pass myData as the object, using the $sign and grams cheese. When we execute this statement, you can find that we get the result as 30. And the degree of freedom is defined as the sample size minus 1. Therefore, since we have the sample size as 30 minus 1, we get the result as 29. In this video, we will talk about confidence level and confidence interval. The confidence intervals measure the degree of uncertainty or certainty in a sampling method. The confidence interval can take any number of probabilities, with the most commonly used being 95% or 99% confidence level. The confidence interval and confidence level are interrelated, but they are not exactly the same. Confidence interval is a range of values that likely would contain an unknown population parameter, whereas confidence level refers to the percentage of probability or certainty that the confidence interval would contain the true population parameters when we draw a random sample from the population. A confidence interval is an educated guess about a certain characteristic within a population. Let us consider the same cheese example. The first statement will import dplyr package using the library function. The second statement uses myData as the object, and using the read.csv function, we will read the contents from Domino's cheese.csv file. In the third statement, we will display the contents of myData object. In the fourth statement, we will be using t.test function. The first argument will be myData, which consists of cheese data, and the second argument we will use is mu to assign the mean. That is, in this case, 100 is the mean. When we execute these statements, you can find that for the 95% confidence level or 0.05% significance level, we have the confidence interval ranging from 95.9417 to 101.4582. So this is how we will be able to compute the confidence interval for the confidence level of 95%. In this video, we will look at the hypothesis testing of the population from a sample. The statistical tests are employed for testing hypotheses about data. For example, specific properties of distribution or their parameters. The basic idea is to estimate probabilities for a hypothesis about the population from a sample. The descriptive statistics can help us identify relationships in data, but the descriptive statistics do not draw conclusions beyond the data samples. Inferential statistics does allow us to make conclusions beyond the data sample, that is, the population. The inferential statistics is the process of drawing conclusions about the populations based on a sample taken from the population. The sample is the data obtained from the population. Hypothesis testing is a procedure in inferential statistics. It is based on the idea that we can express things about the population from a sample. In hypothesis testing, we have null hypothesis. The null hypothesis states that two populations are not different with respect to a certain parameter or property. It is assumed that an observed effect is purely random. And the other is the alternative hypothesis, which is sometimes also referred as experimental hypothesis. The alternate hypothesis claims that a specific effect exists and is never completely true or proven. The acceptance of alternative hypothesis means only that the null hypothesis is unlikely. Whether an effect is significant or not is determined by comparing the p-value of a test with a predefined critical value. If the p-value is less than the significance level or critical value, we will reject the null hypothesis. That is, the sample of the data has given the evidence that null hypothesis is wrong. To perform inferential statistics, we use t-test. A t-test is a type of inferential statistics which is used to determine if there is a significant difference between the means of two groups, which may be related in certain features. A t-test is used as an hypothesis testing tool which allows testing of an assumption applicable to a population. A t-test looks at the t-statistics, the t-distribution values, and the degree of freedom to determine the probability of difference between two sets of data. There are three types of t-test. One sample test, which compares the sample mean to a specified population mean. Two sample test, which compares the means of two independent samples. And paired samples test, which compares the means of two paired samples. In our programming language, we can use the function t.test to perform all three types of t-tests. Let us take an example to understand hypothesis testing. Let us consider that Domino's sells pizzas and they have the offer of buy one get one free on some days to boost the sales. We keep track of sales on all days. We will consider one sample of sales on the days which have offer and another sample of sales on the days that doesn't have offers. To perform the analysis, the first step is to decide the hypothesis. The null hypothesis is that there is no difference between the sales on offer days and on non-offer days. And for the alternate hypothesis, there is a difference in sales for offer and non-offer days. The sales could go up or down as a result of an offer. So the null hypothesis will be sales on offers is equal to sales on non-offer days. And the alternate hypothesis will be sales on offer days are not equal to sales on non-offer days. In the alternative hypothesis, we can have the difference as a positive or negative. This is called as a two-tailed test or exploratory hypothesis. If we rearrange the equation for null hypothesis, we have sales on offer days minus the sales on non-offer days is equal to 0. In the same way, for alternate hypothesis, sales on offer days minus the sales on non-offer days is not equal to 0. The statistical test can only test for differences between the samples and not for the equality. So if we are sure that the sales will not go down and only interested in whether sales went up or stayed the same, the hypothesis will be, for null hypothesis, sales on offer days is less than equal to sales on non-offer days, which is evaluated as sales on offer days minus sales on non-offer days is less than equal to 0. In the same way, for alternate hypothesis, sales on offer days is greater than sales on non-offer days. When we re-evaluate this equation, we get sales on offer days minus sales on non-offer days is greater than 0. So once we are decided with the hypothesis, let us practically perform the hypothesis testing. We will use the Zomino sales.csv file as the dataset, which consists of first column as sales on offer days and the second column as sales on non-offer days. In the first statement, we will import the dplyr package using the library function and passing the argument as dplyr. In the next statement, we will create an object myData and using the assignment operator and read.csv function, we will pass the argument as Zomino sales.csv file name. This statement reads the entire content of CSV file and stores the data in myData object. When we execute these statements, we can find that the entire content of Zomino's sales data is displayed in the output. We will now perform the two-sample t-test using the t.test function. We will pass the argument as myData $offer days and the second argument as myData non-offer days. Remember that the myData object is a data frame. Therefore, we need to use $ to represent columns of the data frame. When we execute the statement, you can find that we get the result of the two-sample t-test displayed. The p-value computed for the two-tailed or two-sample t-test is 0.01814 and the mean sales for the offer days is 307.35, whereas the mean sales for non-offer days is 265.83. The significance level by default is 0.05, which corresponds to 95% confidence level. The computed p-value, that is 0.018, is less than the level of significance, that is 0.05. So we reject the null hypothesis. This means that there is a difference in sales between offer days and non-offer days. The p-value is the probability that if the null hypothesis is true, sampling variation would produce an estimate. To compute the one sample t-test, we will use t.test function and pass myData $offer days as the first argument and mean value as the second argument using mu as the parameter and assigning the value as 265.83, which is the mean sales for the non-offer days. When we execute this statement, we find that one sample t-test is computed and the p-value computed for one tailed test or one sample t-test is 0.002456. So this is how we can perform hypothesis testing in R programming language. In this video, we will look at how to perform chi-square test. The chi-square test examines whether rows and columns of the contingency table are statistically significantly associated. There are two kinds of chi-square test: the test of independence, which asks a question of relationship such as, is there a relationship between two variables, such as ratings and courses? And the goodness of fit test, which asks if a coin is tossed 100 times, will it come up with heads 50 times and tails 50 times? For these tests, degrees of freedom are utilized to determine if a certain null hypothesis can be rejected based on the total number of variables and sample within the experiment. The null hypothesis for the chi-square test states that the row and the column variables of the contingency table are independent, whereas for the alternative hypothesis, the row and column variables are dependent. For example, when considering students and course choice, a sample size of 30 to 40 students is likely not large enough to generate significant data or results. Getting the same and similar results from a study using a sample size of 400 or 500 students is more valid. If the calculated chi-square statistic or p-value is greater than the critical value, then we must conclude that the row and column variables are not independent of each other. This implies that they are significantly associated. Let us now practically look at how to perform chi-square test. We will use an example of ratings data. Let us create an object ratings, and using the assignment operator and C function, we will assign values to the ratings vector. Let us consider that the elements of the ratings vector represent the reviews or ratings of a product given by different users. In the next statement, we will convert the ratings vector into ratings factor, using the ratings object with the assignment operator and factor function by passing ratings as the argument. We will use another example of courses data. Let us create an object courses, and using the assignment operator and C function, we will assign values to the courses vector. Let us consider that the elements of the courses vector represents courses in terms of zeros and ones. In the next statement, we will convert the courses vector into courses factor, using courses object with the assignment operator and factor function, and by passing courses as the argument. Let us execute these statements. Let us now assign the names of the courses to the courses factor using the levels function. We will use the assignment operator, and using the C function, we will have first element as R and the second element as Python. So the value 0 in the courses vector is now represented by string R, and the value 1 in the courses vector is represented by string Python. In the next statement, we will use the table function, passing the first argument as ratings and the second argument as courses. The table function builds a contingency table of the counts at each combination of factor levels. In this case, the contingency table is built for the counts of ratings and courses combination. When we execute these statements, you can find that values of ratings factor represents the rows of the table, since rating is passed as the first argument, and the values of courses factor represent the columns of the table. The values of the tables represent the count of rating corresponding to the courses. We will save these results in an object that is myData. In the next statement, we will use chisq.test function and pass the argument as myData, which stores the contingency table representing counts of ratings and courses data. The chisq.test function computes the chi-square test. When we execute the statement, you can find that the result of chi-square test is displayed. For the Pearson's chi-square test, the p-value computed is 0.5704. Since the p-value is somewhat greater than the critical value or significance value, which is by default 0.05, we conclude that the row and column variables are not independent of each other. This implies that they are significantly associated. You can also find that we get a warning, that is, the chi-squared approximation may be incorrect. This is because data is likely not large enough to generate significant results. We can use simulate.p.value parameter and assign the value as true. This will simulate p-value with replicating the data values of the contingency table. When we execute this statement, you can find that the Pearson's chi-squared test is simulated based on 2000 replicated values. And we get the p-value as 0.72, which also implies that the variables are not independent. So this is how we can perform chi-square test in our programming language.